Welcome back to part 2 of making ultra precision toolroom spindles. Here I'm going to cover some aspects about engineering relative to heat treatment, and in this case we're talking about anticipating the growth that's going to occur when this part is heat treated. All metals aren't the same, but we're going to just focus on what A2 does. So I'm using my Hudson's Metals Tool Steel Black Book to look up the heat treat response for A2, which is the material that we're making these out of. And this chart shows hardness relative to temperature. Rising temperature obviously comes down and gets softer, and then toughness is shown here also, and obviously higher temperature the toughness gets higher. On this side we're looking at size change during hardening, and these are all tempering temperatures, and you can see there's quite a variation of where the material goes to relative to its initial unhardened condition to the hardened condition. And here we're seeing it roughly 200 degrees Fahrenheit, which would be the highest hardness that this would be done at. We would probably get 7.5 10,000ths of an inch per inch of growth. But it's better to historically know from pieces, like taking this piece itself, measuring pieces beforehand and recording what they were, and when they come back measure what they are, and we know historically that A2 actually has a tendency to be more closer to 1,000th of an inch per inch, or 0.1% growth. So all of the dimensions on everything I make in this are compensated to be 0.999, the actual dimensions, so that when it's heat treated, it's actually at the sizes that we want. So we're making it smaller because it's going to grow, and that's what you have. Another important thing that I mention often is you don't want hardness tests in the part. Most heat treaters will not. They have to do a test on their parts. They're not allowed to not test. But you can send a test puck and say, test on the test puck only. So a piece of the same material, I don't typically worry about it being the exact same material, like from the exact same bar. If it's A2, it's A2. I'm not typically worried about super precise Rockwell values, so I don't worry about it. But you send a piece along, make sure it's got smooth, flat surfaces, because that can influence the hardness reading if you don't have a good bearing on the anvils when you're testing. So good tip, send test pucks, put on the order. Do not test parts, test puck only, and you're good to go. Method of heat treat. Vacuum hardening is relatively inexpensive. I realize for hobbyists that's easy to say, but a minimum batch for the people I use, Solar Atmospheres, is $105, and you can get a lot heat treated for $105. That's vacuum hardened, air tempered. What that means is vacuum hardening is done in a vacuum chamber. It's taken up to temperature through the recommended cycles for the material, how long you take it up to what temperature, let it soak, and then carry up to the actual heat treat temperature, and then the quench. Well, in the vacuum furnace, the quench is actually done with a high pressure gas that's recirculated through the heat treat oven, and has a heat exchanger on the outside to rapidly remove the heat that it's absorbing out of the parts, take it out of the gas, and when it goes back in again, it's chilled. So you're basically running cool gas past the parts to bring them down to temperature at the rate required to harden them. All materials can't be done. There's limits to how rapidly the quench rate can be using gas, but they can do pretty good. But some materials just their quench rate required, as an example, water hardening tool steel. You can't send that out and have it vacuum hardened because the quench rate is too slow. Because water is a very, very quick, rapid quench. But everything else, vacuum heat treat, works really well and is relatively economical. And the parts don't get moved from their position. When they're staged so that there's circulation around them, and the gases circulate evenly. So these parts rarely have any distortion that can amount to anything. Very, very small distortions on these parts. It doesn't mean that there aren't things that have to be straightened and whatnot, but as things go, it's definitely the safest heat treat method. This is an example of the type of thing I'm talking about. very thin wall shell. This is the collet nut and collet nose for the smaller spindle, and has a very thin wall. This thin shell has virtually no distortion, as does this. Nice and round, nice and uniform, just because everything is extremely uniform about how they're heated and quenched. So yeah, just big pluses for that. It's also a chance to show the actual coupling setup here that is the nut system that I'm using here, because these actually stick together. That 2 degrees taper that I showed on how these were done, these engage, and there's no tendency to slip out. This actually engages, and if you tap it, it'll actually stick fast. You can see that's held just because of the tapers matching. So this is the actual wrench to tighten the collets in both cases. This fits this one, as you can see that one's tight, and fits this one also. Same situation. This is the larger spindle.
When you have precision parts like this to be sent out for a service like heat treat or anodizing, it's very important to make packaging that allows the people doing the job to easily be able to put the parts back where you want them with basically no instructions. You can't expect them to wrap pieces like you would wrap them. So fitted packaging like I've shown here is just extremely important in getting your products back in pristine condition without any nicks or dents.
One more little side note about heat treatment. Heat treating a steel that is hardenable only moves its yield point and changes its hardness. It does not change the modulus of elasticity of the steel. So modulus of elasticity just meaning if you have a beam sticking out a certain amount and you put a certain weight on the end, how much does it deflect? That amount of deflection won't change whether it's fully hard or whether it's soft. But the amount of weight that it can take before it takes a permanent set and does not spring back to its original condition does change. That's the yield point. So it's very important to realize that steel is not stiffer in its heat treated condition. Its yield point has just moved, meaning it can take an immense amount more force before you permanently deform it.
So here is how the blind mounting system works on my toolroom spindle. This is the larger toolroom spindle that has this mounting method. This is the eccentric pin you saw from before that we've made. This is my 4 3/4 inch magnetic chuck, and then I come over here and this is my 10-inch magnetic chuck, and this goes in the same way, and these lock up. These have allowance for needing to grind some off the face of the spindle when it's done. So these don't actually rotate around far enough. These have to be obviously in the 3/4, from 90 degrees down to the bottom, just like a D1 spindle on a lathe. So once I grind these will be in the correct location where they'll start to lock up at 90 degrees here, and then as it sweeps down through to the bottom, it will be full tight.
Here we have the parallel sitting across 2 pins that are 180 degrees apart, meaning that this is the center. But I actually want to drill the hole in this pin off a little bit so that we can crack it loose when it's aligned to the center. So I'm doing that by moving over 1 pin like that, aligning the bar that we put on here so that the hole goes through like this. So now I just put some super glue gel on top here, take my block that I've degreased, hold my parallel tight, press down on top here and press it over. Give it a little time to cure, like that. Break this loose. Take this over to the mill, and we'll drill the hole. Here's that same pin over here in the setup in the Bridgeport for drilling the hole. Got just a piece of scrap cold rolled here with a hole drilled in it to clear the threaded part. So this is just a slip fit. This is just a reference shoulder, so I can have a fixed distance. I've edge found over here, got my .240 distance out to the center here. This is the piece that we glued over on that you saw. I used a 1, 2, 3 block here against that as I clamped. This is just another jaw in here to act as a spacer to clear my 2 vice grip clamps in the back. And then on each one, since this is a variable position, I edge finder off the back and move to the center on each one, and take the drill, just a regular screw machine drill, a solid carbide 5/32 end mill to go through, and then this is a hand done, hand slash single lip cutter grinder job where I turned a 1/4 inch end mill into a 60-degree piloted chamfer tool. The reason that I use the pilot is because I can do this side in this position, but then I have to do the other side freehand in a V-block, so the pilot will maintain position. So here we just broke off the glued joint, and we're going to put this back in because we need it for positioning the next piece. And if we check, we can say, okay, tightened. This drill is past center here, showing that it's over, and that means that when it's cracked loose, it will be on center so that this pin can float and get centered in the spindle nose. Here's a technique that wouldn't be recommended for mass production, but for specialty tool room items. One technique I like to use is turning the heads of socket head cap screw to a nominal size. In this case, I turned the head of an M5 socket head screw down to 5/16 of an inch, 0.3125, from its original 0.359, I believe, diameter. The purpose of that is so that I can do a very precise fitting counterbore that only has a few thousandths of clearance. These only have like about 2 thousandths clearance, and several things that does. It leaves these with the maximum material possible. It does not really decrease the strength of the screw at all. And it leaves a situation where this can be sealed by just using some wicking Loctite number 290 after this is installed to seal that gap so that coolant doesn't get in there, grit doesn't get in there and cause corrosion problems, and makes it easier to blow these things off when they've been covered with grit and coolant and been in service. So important feature. It's sometimes even for just clearance reasons. You can see here that the clearance between this and the mounting screws, if I did in a normal size counterbore, this screw couldn't exist. And just by trimming these heads down, I got to a situation where these could be where they needed to be and not be a problem.
Extra clamps on the punch grinder to make it seat on the chuck a little bit more firmly other than just gravity, and that also blocks the grinder in so it can't skid on the chuck. And this allows the differential screw setup that we have here on the back allows very precise tilt adjustments, easily 1 arcsecond or less adjustments of tilt so that you can get it adjusted to get a very flat grind. In this case, I was easy to get within about 20 to 30 millionths flatness over that 5-inch diameter. I have all my tool room spindle parts that many of them are ideal candidates for this rotary spin grinding, which can give very good results, better than the normal XY normal surface grinding, and obviously the round parts require the rotary aspect. So I'm going to grind up these parts.
This is a Ryobi screwdriver that I have taken the handle off of and put a bearing system in the front to drive this punch grinder, and I'm using a old Power Designs power supply for variable speed driving the motor, which works very nicely. I've fully automated this Harig grinder using micro stepper motors. Those hand wheels have encoders acting as manual pulse generators, and then I have various screens, 2 screen locations here where I have various things programmed for automatic cycles and just general use of the grinder. So let's talk about rotary grinding a little bit. And obviously that's when we have a flat spin table here, a bearing system that rotates a magnetic chuck or a face plate in this orientation such that when we traverse in these directions like this, we can grind a circular path, and we can put round parts on, but we can also put parts on like this where we have a square cross section. But this minimizes the actual grind time because compared to traversing this and cutting air a lot and also having vastly varying areas of engagement. Rotary, we have at least uniform engagement here and then out to this, so the amount of actual wheel in contact with the part time goes way up when you're rotary grinding parts like this, or cylindrical parts. So that's the advantage of the rotary grinding. It can also give you inherently more parallel parts because you can grind the chuck, and then this surface will be running on its own bearings. It will be as good as the bearings run, and it'll be true to that bearing system. And if you've got reasonably good bearings, you can get very parallel parts just by truing your chuck and then grinding the parts on there. Now, geometry. The axis of the spindle, whether it tilts like this or this, is actually going to determine whether or not you grind a concave cone, convex cone, or grind a perfectly flat part. That's why the tilt adjust of these needs to be able to adjust in very fine increments and repeatably if you want to be able to tune your grinder in to grind very flat parts. On the same token, you have to be very careful when you're getting down to very small numbers about the wheel wear, the change in surface footage from here to here in the actual part surface footage as it's spinning. You got very slow surface footage here, higher here, material removal rates higher here. All kinds of dynamics are involved, but if you're careful, you can get very, very true parts with this, and also, like we see in the examples in this video, of grinding round parts, grinding up to a shoulder, things like that. Why can parts off of here be generally flatter than on the surface grinder? Well, in this, the only thing that controls the trueness of the surface ground along here is the trueness of one axis, the z-axis of the grinder moving in this direction, back and forth. So however straight that is, that's the only axis that's in motion other than this rotary axis. And this rotary axis typically is going to be a lot more accurate than the traverse can be on a grinder, because the traverses on a grinder can have roll and yaw and twist and things that will cause the surface to not be flat. As you traverse across, you can end up with a part that has an actual twist in it because the grinder is grinding with a twist. As long as one axis, the z-axis of the grinder here, is reasonably straight, you're going to be able to get a part that is very flat. Now, flat meaning parallel in a sense, but if you adjust all the conicalness out of the part, if you want to call it that, and get it to be where it measures the same thickness out here and in the center, then you've got parts that are extremely flat. So it basically enhances the ability of a grinder to produce very parallel cylindrical parts better than you can do in the chuck. And the other aspect of grinding, when you're reciprocating grinding, if you have a grinder that's using oil film, the speed of the traverse affects the actual oil film height. Yes, we're talking very small numbers, sub-tenth numbers of difference in oil film height depending on your traverse speed, but it's there. So that affects the shape of your part also. So a ball bearing style or an air bearing style of rotary spindle can give you very, very flat parts. One very important aspect of the precision grinding at this level and trying to get very good finishes and geometry at the same time is thermal growth of the column of the machine as it warms up. In my case, my grinder, the spindle runs hot because I have poor quality of three-phase coming out of my phase converter. I have a VFD that I plan to put on, but at the moment it gets pretty warm, and that puts a lot of heat into the column until it settles out. It probably runs about 110 degrees. I have it fan cooled, but it still generates heat. And in the background you can hear a trickle going on, and that's the lubrication system in the Harig grinder that's continuously pumping oil up to the top of the column, and then it runs down through, lubricates everything, lubricates all the ways, and that oil generates some heat as it warms up. Probably warms the grinder column up about 5 or 6 degrees from ambient temperature from that oil, just the oil shear effects and everything in the pump that causes that heat generation. So when you're trying to remove very small amounts of material, or you want your grind height that you've just dialed in to actually remain consistent, if the grinder's not totally warmed up where everything's thermally stable, the column is growing. It's getting longer from the base up to where it's supporting the grinding wheel. And in this particular situation here, where we're grinding on the setup here, there's roughly about 17 inches between the base and the spindle of the grinder. And let's just pick a round number of, that's six micro inches per inch per degree Fahrenheit growth of steel or iron. It's roughly close to that. For 1 degree rise out of 17 inches, that's 1/10,000th of an inch of rise of the column. And so any thermal changes that are occurring while the grinder's warming up, the column's constantly growing up away from the part. So when you have a grinder that's capable of downfeeding very small increments, 50 millionths, 10 millionths, 5 millionths downfeed increments, you can be fooled because you take those amounts, but it doesn't take any material off because the column is growing away at a larger amount than that. So that's one of those, this grinder takes probably a good half the day to warm up and stabilize. And if I'm doing work where it's very precise, I will not shut the grinder off overnight. I'll leave everything run, leave it just continuously run with the oil running and everything on so that it's completely stabilized, then things stay put. Some may say you're talking about 10 millionths, 5 millionths, whatever, 20 millionths downfeed increments, and hogwash. That's just an ordinary old Harig grinder with scraped ways, and you got stepper motors on it. You can't get those kind of downfeed increments. And if you do everything properly, you can. And number one, the scraping and the finishing of the scraping on the column ways of this are extremely precise, and they're lapped, and to give it extremely precise oil film that's consistent. And there's weights on the spindle system to minimize the moment loads on the weigh system, so that it's just traveling vertical. But the real key is to not expect the machine to move just a single 5 millionths inch move or 10 millionths inch move, and that's because of stick slip, of static friction, and that breakaway. So with a programmable machine, by moving up, let's say 50 thousandths, and then moving down 50 thousandths and 10 millionths, you basically have changed the lubrication and the motion regime into the dynamic friction realm, and you can easily do these motions. So my downfeed button that I hit, which is, I can program anything I want in 5 millionth increments up to like 5 thousandths of an inch per increment. I just have it limited that for safety purposes. It does exactly what you say. Is it exactly 5 millionths or 10 millionths? No, it might be 9 one time, 11 the next, but it's close enough for what we're doing here. But there's an example of just using a very simple principle of getting it out of the static mode and running uphill, downhill. You get your oil film, moving, and you're in the dynamic friction mode, and it repeats extremely well. And the mechanical resolution of the system with the micro stepper motors is 5 millionths on the vertical. Here I will do an incremental feed, and you'll see it moves up about 50 thousandths and then down 50 thousandths, and in this case 50 thousandths and 50 millionths, because I'm doing a 50 millionths down feed. So that's what it does. Do it again. You can put in a negative value to go up if you'd like, so it's easy to go back up an exact amount, but it works extremely well. So when you hear me talking about taking 20 millionths or 30 millionths or whatever, I'm not blowing smoke here. It really does respond that way. And it's also a way to be able to see exactly what's going on. And I always put the purple Sharpie on between cuts so that I can actually tell whether or not whether the column's still growing away, because obviously you can't always wait for the machine to stabilize, so I actually run with it warmer. So there's often times while it's warming up that I'm in order to get it to take a 10 millionths cut, I'll have to do 20 or 30 millionths down feed to get it to actually cut the Sharpie marks off there, and to know that you're actually taking a finish pass. And with normal grinding, slowing the actual traverse rate of the path across the part, in this case working radially out off the part, when you slow that way down, you can get greatly improved finishes. but it also increases that thermal time for it to grow up as it's doing that, changing the shape of the part. Now these parts are going to get lapped where it's important anyhow, so it's not critical that they're perfectly flat as ground, but the closer they are, the easier it's going to be to lapping it. And it's always fun to just practice on getting good geometry as ground. Another important aspect to keep in mind when you're talking about very high precision grinding is, as you've heard me say many times, everything is rubber, and the entire mechanical loop of this grinder, meaning from the grinding wheel back through the spindle, down to the column, over to the saddle, up through the saddle to the table, up through the actual rotary spin table, and in its bearings, all of that is the mechanical loop, and that has a certain spring rate, meaning if you push up on the wheel with a certain amount of force, you're going to get a certain amount of deflection, and also increasing the load on the table is going to have the table deflect some. So there's always deflections involved. And I'm bringing that up because of talking about a situation here where or in any grinding, and this rotary just points out a situation where it's easy to get a good example to explain a phenomenon. When the grinding wheel is engaged here, it's got a continuous bearing, meaning it's engaged with the part and it's actually pushing on the part, trying to cut continuously. And when it moves out here, where it's off the part, but it engages this intermittently, 4 times per revolution in this case, it climbs up onto the part. You have a situation where here it's loaded continuously, but here, as it comes off the part, this can actually unload and drop because it's not sprung. But then when it comes here to grind up, there's mass to this whole system. And as it comes across here and the part tries to push the wheel up because of the resistance to grinding, it can't move that grinder spindle up as quickly as it needs to. It's going to actually be grinding lower here where it had to jump up than it is here where it was continuously loaded and just held up. So what you'll find is where you have the grinder this tweaked in to be grinding perfectly flat, you'll find that when you're doing your roughing passes and everything, this will be high here and low here. And if you're roughing and really barking the material off, as I did in some of these, you'll find that it can take this might be 5/10,000ths of an inch lower than here, just from this phenomenon of what I'm talking about here, where this is unloaded, loaded, and this impulse cut, where the wheel basically has to jump up on here because of the loading, causes it to grind deeper. Now, there's a lot of things involved in how much cutting pressure there is. The wider the engaged wheel width, the more pressure. So if you're out to get the most accurate results from the grinder, then sometimes narrowing your wheel width for that condition, especially on hard to grind materials, can give you more accurate results. But then you have the situation where that narrow wheel width is also going to wear faster. So now you have to consider wheel wear in the traverse of the parts depending on how much surface area you're grinding. So it's always catch-22 on what works there. The other thing is how you dress the wheel and how much the wheel has been used, or how much the wheel has worn and how dull it is. A lot of people use coarse wheels and dress them fine, and that automatically creates a situation where the pressure that it takes to initiate a cut on the wheel is higher than if the wheel was really dressed what it's designed for, meaning dress it to cut with the grit size that it is. Don't try to dress it fine and get a shiny finish. Shiny finish, the shinier it gets, typically means the more that wheel's burnishing instead of cutting freely. So there's a trade-off there. It pays to use much finer grit wheels that are dressed properly, meaning open, like use a 150 grit wheel or a 220 grit wheel sometimes, to get the finish you're after without dressing the wheel in a glazed condition. That sharp wheel is very important for this high precision stuff, that it can cut freely and the amount of pressure needed to initiate a cut is very low. So that's a trade-off to keep in mind, and also to think of the dynamics that This wheel head's not infinitely rigid. It responds to the cuts that it's going on. It has to climb up onto the part and down again. So that's where the keeping those considerations in mind is important. Also, if this was just a cylindrical spacer, you have the situation where, and people are probably familiar with this that have ground much, is when you come off the part, the engaged with the wheel is changing as you get off the part. So if we were moving over here and we're on this side, the edge of the wheel starts on, the full wheel width is engaged and off, you can have a tendency to have a curved situation on here where the grinder grinds higher when the full wheel width is engaged, and then as the edge of the wheel tails off and the engaged width keeps decreasing, it's able to grind deeper and deeper because there's less and less wheel to support, and the wheel actually flexes down into the part deeper on each side of the cut, on each side of the part. So just something that lots of grinder people that have been doing it for years know all about this, but that might be something for people who are new to surface grinding to really think about the dynamics of what's going on in the grind, because that just lets you do a better job of analyzing what's going on. So that's why grinding's somewhat of a art rather than exact science, because there's just so many variables involved in what you end up with. And having a clear picture of how they all interact and which ones may or may not be the major contributors in your setup can be very helpful. We're going to check the 4 sides and where it's the thinnest here. Here's 0, 90 degrees, plus 30 millionths, plus 10 millionths, minus 10 millionths. See what our repeat is like. Pretty good. 0. Now I'm running over the 4 corners, looking for the amount of change from inside to outside. Very little there. Probably 10 millionths. Maybe 20 on this one. Nice 10 millionths there. And that's low in general. That's low, probably 20-25 millionths from the other zeros, but still well flat enough for what we're doing. This is a perfect example of the use of the magic sanding plate to make sure that the surface you're sitting on is basically flat enough that it will not warp when it touches down on the grinder and the chuck pulls it down tightly. So this is flat enough that you can put this on as is, not have to worry about it being out of shape and being warped enough that when you release it from the chuck it springs up and gives you a different size. So it saves an immense amount of time, lets you see what's going on. I'll indicate this in by looking for our high point, tapping it in to basically halfway mark between the sweep and the variable speed control lets me just drive this. I'm turning the knob down here on the power supply. That's plenty good enough for grinding. Then I'm going to stop where the place is to turn the chuck on, and we'll touch off and grind. I have places to electronically set the Z plus, the Z minus locations of where my automatic grind is going to traverse across, and the X plus location is when it lines up with the center line of the spin fixture, the wheel does. X minus is where it retracts to. So I'm above the part, and I can crank to my Z plus setting. That's where it's going to run off the part on the one side, and run across to the Z minus location where I'm just off the part on the inside. Set my Z minus, and that's going to set where everything is, and I can jog back. Here's what that grind cycle runs like. Gets in the correct Z minus position, runs up to the center of the chuck in X, traverses across at whatever feed rate I have set, so it gets to the Z plus position and retracts.
Here's the first grind pass. It's taking off enough to make sure where we are. It's just traversing across at a fixed feed rate that's set on the control panel. Wraps off. Now down feed again, and this is at 8x speed, and we're taking 2 more cuts to clean up.
Release the part. Use a lever, plastic lever, to break it loose from the chuck. That's a pretty nice grind. That's a 60 grit wheel.
Here you see the bubbles from the air purge system that I have in the punch grinder to keep the coolant out of the bearings, and the regulator and hose that apply its power. This is the coolant system. Got a 5 micron felt filter bag in there, and some other filters in those household cartridges that do a pretty nice job. This parts washer brush that I can clip on instead of the coolant nozzle is really great for washing down the grinder to clean everything out.
So this is the untouched face of the part back from heat treat. I'm going on the magic sanding plate to see what it looks like. Changing positions. And we'll come up and see what's going on. We can see heavy here, might not be easy for you to see in the camera, but light out here. But this is bearing enough that it's going to touch on the chuck evenly and not cause any distortion. And this cross section here is thick enough that it's not going to do much anyhow. Here's our 5-inch Toolroom spindle body. But the problem here is this hole completely misses the magnetic lines of flux in this chuck. So what are we going to do? We have this fixture plate that I use grabbing a 1-inch collet here and bolting things on the lathe. So this is nice and flat, been on this magic sanding plate, has a 3/8/16 tap hole, and this fits inside that housing without hitting anything. So I'm going to put this on the magnetic chuck and then use a cover plate inside to just physically, mechanically hold the part touching this outside band. So basically clamping it to the face of the magnetic chuck, even though the magnetic flux is not running through the part itself. It's simply holding this on. So I've tapped this in to run with 1,000th or so, which is severe overkill. Doesn't need to be that good. Here you can see I have that indicated in within a few thousandths, which is plenty, and I will grind that upper face.
These are lighter finish passes that I'm doing in this view. This is at 2x speed.
That's not too shabby a finish there. We flipped it over, indicated it in, snugged the screw, and we're ready to grind the other side. Side 2 finished. For the final passes, I slowed my rotary speed way down, and what that does is it lets the whatever amount of out of balance there is still left in the wheel, even after balancing, it allows the scallop from that, basically the high point touching, which still shows up unless you're absolutely perfectly balanced, which this isn't. It's balanced very well, but not to the point where you don't have some hop showing. slowing the traverse makes those scallops occur much closer together. And then my traverse rate across the part is also very, very slow. It's half an inch a minute. And I can still hear it grinding, so this was a 30 millionths cut, but you don't know whether it's actually 30 millionths or not because the system still sprung some. So I'll take 2 spring passes in this location for it to be able to truly relax and remove down to the minimum amount of material, and that will give a really good finish. You still have to remember that if the wheel is a little dull or whatever, you could get some shape from the intermittent cut and the change of shape, but I think where we are here will be pretty good.
Ooh. Generally, when doing parts like this with a larger face and a smaller face, it pays to reference off the large face and grind the smaller. This will generally give you less material removal required to get parallelism. There's the larger face ground parallel to the smaller face we did earlier. And here we're doing a painfully slow finish pass. 0.3 inch per minute and 10 millionths down feed on that pass. Finish this side. Now we'll flip over and hit this face and get it cleaned up. Oh, nice finish on that.
10 millionths per division on the upper scale, the black scale. 0 to 1 is 1/10,000th of an inch. Moving in towards the center, top of the counterbore, back out again. Yes, the indicator really is moving. You can see there I'm going to check 4 spots around here just for parallelism. We're zeroed on this spot. 90 degrees. 50 millionths. 25 millionths. 30 millionths. Back to our 0.
Here I'm relieving the side of the wheel because I'm going to be getting down close to the shoulder, full length shoulder, and I need to clear this out so it doesn't run into the part. Here I'm touching off my Z position on the control for where it's going to stop and start its grind position. Here it's down feeding and traversing off the part. That's the automatic cycle. And now we'll see an overall view of it. Up and down, they just did there for the actual down feed increment. Moves into the Z position, comes in, feeds down, dwells, and then slowly traverses across the part at whatever feed rate you have until it reaches the Z plus stop position that was set and retracts. Here you can see the purple Sharpie has been removed by the wheel touching down, and it's barely touching. It's maybe 10-15 millionths that is taking off there, but it's enough to remove the Sharpie, and you can see each revolution as the wheel's moving out, it's cleaning off that Sharpie. That's how I can tell if I'm actually down feeding and touching the part while the grinder's still warming up and the column's moving. There's the bearing race surface that was ground, and the seal surface that was ground, and the upper bolting surface that was ground.
Here we're measuring the back clamp face that we did first, actually. There's 0 there. 10 millionths. 5/10 millionths. 5/10 millionths. Back to our 0. You'll notice down here that we've got some taper, or it's conical. It's high in the center, low on the outside. and that is from the fact that I'm taking a full half-inch wheel, diving in here and moving out, and that's not an ideal situation. Where these other surfaces we could get completely off on the inside, use the full wheel width, so none of the shape of the wheel got into the grind. But that doesn't matter because it is going to be lapped anyhow. So what I'm doing here is I've got a mark there so I know when I've gone a full revolution, and we can just watch up top and say, okay, what's our TIR look like as far as facial TIR? And that's probably well within a micron, 40 millionths there. So that's not too bad. Plenty good enough for where we are in this stages of building this.
Indicating in the smaller spindle, and there's a smaller spindle ground in. As always, finding some feature of the part to be able to lever the part off the chuck. Grinding the seal surface on the rear plate.
That's it for this video. What's next will be grinding the outsides of these, the outer four faces of the housings, hard turning the bore and faces here where the bearings ride, hard turning these surfaces, the cylindrical diameters here where the bearings ride, and that'll probably be it for the next video. Hope you found this interesting, and I'll be back.